one of the graphs algorithm, that is Bellman-Ford algorithm. So we will be learning this algorithm. Before that, we will be knowing what are the main uses or applications of this algorithm. Very first use is to find the shortest path from a single source. What do you mean? What we mean by that is that हमारे पास एक ग्राफ है एंड उस ग्राफ में एक सोर्स से टू द अनदर नोड्स टू द अनदर वर्टिसेस पे पहुंचने के लिए जो हमारा शॉर्टेस्ट पाथ होगा via weight, that is the main point, via weight of the edges, कि हमारी जो एजेस है उसका वेट कंसिडर करते हुए हमारे एक सोर्स से दूसरे नोड पे दूसरे एज पे दूसरे वर्टेक्स पे पहुंचने में हमारे कौन सा पाथ होगा दैट विल बी द शॉर्टेस्ट हैविंग द लीस्ट वेट. That is the one of the application of this. Second, to detect the negative cycle in the graph. What do you mean by negative cycle? I will be telling you that there are two nodes 0 and 1 that having 1 -1 and -1. So basically हमारा क्या होता है कि अगर मैं 0 से 1 पे जाऊँगा तो वेट इज़ रिड्यूस्ड. फॉर एग्जाम्पल इट्स 0 एंड इन्फिनिटी. दैट मैंने क्या किया 0 -1 इज लेस देन इन्फिनिटी. इट विल बी अपडेटेड टू -1 -2. तो अब हमने क्या किया 0 से 1 पे गए 1 से 0 पे आए दैट इज़ -2 और हमारा जो वेट है वो डिक्रीज हो गया. अब मैं अगर इसे कॉन्टिन्यूस वे में चलाता रहूँगा 0 to 1 1 to 0 द वेट विल कीप ऑन डिक्रीजिंग एंड देयर इज़ अ नेगेटिव साइकिल. तो हमारा ग्राफ में एक नेगेटिव साइकिल है या नहीं उसे डिटेक्ट करने के लिए भी हम बेलमैन-फोर्ड का यूज़ करते हैं. नाउ वन ऑफ द वेरी बिगेस्ट क्वेश्चन व्हाइल डूइंग एनीथिंग वी शुड हैव इज व्हाई वी नीड दिस. व्हाई वी नीड दिस एल्गोरिथम. जैसे कि हम जानते हैं लाइक प्रीवियसली इफ़ यू आर वेल नोन अबाउट BFS, DFS एंड Dijkstra's, सो वाई वी आर एनकाउंटरिंग विद दिस पर्टिकुलर एल्गोरिथम. जब हमारे पास वो दो एल्गोरिथम्स हैं BFS एंड Dijkstra's टू फाइंड द शॉर्टेस्ट पाथ फ्रॉम अ सोर्स टू अ particular destination, so why we need this algorithm. So very firstly we will be knowing about why not BFS. Why not BFS का आंसर अगर आपने Dijkstra's पढ़ा है you will be knowing कि why not BFS. अगर हमारे पास BFS था तो हम Dijkstra's पे क्यों आए. तो इसका आंसर होता है why. इसका आंसर है इसी में लाइक BFS इज ब्रेथ फॉर सर्च, जिसमें हम क्या करते हैं वी आर ट्राइंग टू फाइंड अ शॉर्टेस्ट पाथ फ्रॉम अ सोर्स टू डेस्टिनेशन बट डिपेंडिंग अपॉन द नंबर ऑफ हॉप्स. उसमें क्या होता है द BFS is trying to find the source shortest path from a single source to a particular destination considering the number of edges in between, not the weight it is taking. So it keeps on considering the number of edges that should be minimum, not the weight of that particular path. For example, if I am having 0 1 2 and here 1 2 and 5. While coming to the BFS, the shortest path for 0 to 2, the source as 0 and the destination to 2, the shortest path will be 0 to 2, 0 to 2. That is having the weight of 5. But the minimum weight to reach 0 to 2 is 0 to 1 and 1 to 2, having the weight of 3. So why not BFS is why because BFS considers the path according to edges, not the weight. Now second one, Why not dextrose? The why not dextrose is because is one of the application of Bellman food, because it cannot work with negative edges or negative cycles in the graph. Now we will be considering one more example for this. For example, I am having a graph similarly taking the above example 0 1 and the weight is -1 and -1. So हम क्या करते हैं हमारे डायस्ट्राज में कि हम एक प्रायोरिटी क्यों लेते हैं, दैट इज़ अ मिन हीप जो हमारी मिन हीप होनी चाहिए, वेयर वी विल बी पुशिंग द पेरेंट एंड इट्स वेट दैट इज़ 0 and 0 एंड हमारा जो नेक्स्ट होता है हम क्या करते हैं उसे पॉप आउट करते हैं एंड उसके बाकी नोड्स को विजिट करते हैं. 0 से हम बाकी नोड क्या है 1 पे हम गए तो वट विल इट बी अपडेटिंग 0 0 प्लस -1 दैट इज -1. अब हमारा न्यू वेट क्या हो गया -1 and 1. नाउ इट विल बी सीइंग कि वो अपने बाकी नोड्स इसके चाइल्ड्स को अब कंसिडर करेगा. अब इसका चाइल्ड क्या है 0 बिकॉज इट इज़ अ अनडायरेक्टेड ग्राफ दैट बोथ कैन रीच बोथ. तो हम 1 से 0 पे गए तो इट इज सेइंग 0 -1 to -1 दैट इज -2 विच इज लेस देन द present weight that is 0, so it will update to -1 and now it will again push into the priority queue and that cycle goes on and it will lead to the infinite loop and the code will dump. That's why dextrose cannot be used in negative edges and the negative cycles. So that's why Bellman food comes into the consideration. Now now we will be knowing about the Bellman food. So the very first advantage of Bellman food is that it works with negative cycles. Cycles. Now what is the basic logic behind the Bellman fold is we relax all the vertices v minus 1 times, where v is number of vertices over all the edges. हम क्या करेंगे हमारे सारे जो वर्टिसेस हैं हम उनको v-1 टाइम रिलैक्स करेंगे. नाउ वी यू सम ऑफ यू माइट नॉट नो व्हाट डज द रिलैक्सेशन मीन्स. फर्स्टली व्हाट इज रिलैक्सेशन? Relaxation is the term used for redefining or updating a particular weight of a vertex from reaching to its parent, and parent can vary from one to another. If there is multiple paths from going from one vertex to another, there is a possibility that the weight might change or update. That is known as relaxation. So if for example if I am having this node 1 2 1 2 and 0, infinity and infinity and 5. So for example if I am going from 0 to 1, the weight is updated to 1, the vertex is relaxed. Here is updated or relaxed. 0 to 2, the path is now again updated, that is we are relaxing the values. So what do you mean by relaxation? That is updating or making changes into the particular vertices or vertex weight is known as the relaxation. That is to minimize the particular weight to reach or particular distance we what will be saying. And now why only v-1 times? This is one of the major question asked to me and maybe many other peoples in their interview. In Bellman food, why the relaxation of vertices should be v minus 1 times. So the answer to this is because if the vertices are interconnected, all if all the vertices are interconnected, a vertex will be connected to v minus 1 vertices. So अगर हमारा एक पर्टिकुलर ग्राफ है in which all the vertices are interconnected, for example here it is a graph, there is just an example and एक अगर मेरे को इस ग्राफ पे पहुंचना है तो there are 4 multiple vertex it can be reached. तो अगर मुझे इस वर्टेक्स पे पहुंचना है या फिर इस वर्टेक्स पे आने के मेरे पास कितने पाथ्स हैं 1 2 3 4, दैट इज 4 एंड टोटल नंबर ऑफ वर्टिसेस वर 5 एंड टू रीच इट वी हैव v minus 1 दैट इज 4 वर्टिसेस. सो अगर मेरे पास एक कोई ग्राफ है जिसमें ऑल द नोड्स आर इंटरकनेक्टेड, सो देयर इज द maximum so v minus 1 vertices are the maximum number of vertices that to which it will be connected. So there is the possibility of updating the weight v minus 1 times, क्योंकि अगर मेरे को एक पर्टिकुलर वर्टेक्स पे पहुंचना है तो मैं v minus 1 तरीकों से पहुंच सकता हूँ और उस v minus तरीके में v minus 1 टाइम्स ही उसका वेट को चेंज होने की पॉसिबिलिटी है. दैट्स वाई वी आर रिलैक्सिंग अ पर्टिकुलर नोड v minus 1 times. Now next point we will be seeing is points to consider before applying Bellman Ford algorithm. So there are 3 major points to remember before applying Bellman Ford. The very first, the graph should be a directed graph. If you are given an undirected graph before applying Bellman Ford, firstly convert it into a directed graph. For example, if I am giving a node like this and I am giving 0 1 1, then I have to make it undirected graph by increasing the number of edges to like this. So the very first condition for before applying Bellman Ford is the graph should be a directed graph. Next second point, we have to relax the vertices v minus 1 times, not more not less, because I have already given the reason why v minus 1 times, because there is the possibility of a particular node can be reached from v minus 1 different nodes. Third point to consider will be the third point to consider will be don't change the order of iteration of edges during relaxation. What do you mean by that is, if I am given a particular order of edges like 0 1 1 and 1 2 0, whatever it is given, if I have started doing in a particular order, that order should not be changed in between while relaxing the v minus 1 times, because there might be a possibility कि एक जो particular edge है वो एक particular vertex को किसी एक मैनर में रिलैक्स कर रही है या अपडेट कर रही है वाइल आइट्रेशन, एंड देर इज़ अ पॉसिबिलिटी अगर मैंने उसका ऑर्डर चेंज कर दिया द आंसर माइट चेंज, बिकॉज देर इज़ अनदर पॉसिबिलिटी वो किसी और एज से उस समय चेंज हो जाए या अपडेट हो जाए. फॉर एग्जाम्पल 0 1 2, let's take one more, and 3. 1, 2, 3, minus 1. For example, this is the only, and if I am doing in the order 0 to 1, 1 to 3, and 1 to 2, and 2 to 3, the answer will be 1, 0, 1. Here it will be 3, and here it will be 3. But now if I am going here to here, the answer should be 3 minus 1, that is minus 2. But before that, if I have changed the order, plus 2. But if before that, in the second iteration, if I have changed, for example, there is one more here, that is minus 5 or something, that might be in another sense, like if it is minus 1, then 2 minus 5 will be minus 3. Here, if now I have changed the order of this particular one, here it will be minus 3 plus 1, minus 2, minus 2, and 2 is 0 और any sense. So there is a possibility कि हमारा जो आंसर है उसका मैनर चेंज हो जाए. So make sure that while iterating over v minus 1 nodes, the edges order should not be changed. If you had taken a particular order, it should not be changed to any another order. Here in this example, it's not changing, but there are many examples I am not getting in. There is a possibility that answer might get changed. Now we will be learning about the Bellman fold. For example, we have having a graph 0, 1, 2, 3, 4, and 5, 5, minus 2, minus 3, let's say. Here it is 1, 3, and minus 1, 5, minus 2, 3, 3, 4, minus 2, and let's say it's 1, minus 2, minus 3, 4, minus 2, 2. And it be 5 minus 2, 5, it be 1. Here the very first thing we will be considering will be order. Let's say we have taken the order like 2, 4, and 1, 4, 5, and minus 2, 0, 1, and 5, 1, 2, and minus 2, 1, 3, and minus 3, 3, 4, and 1, 3, 5, and 2. Is it visible? Sorry. It will be 3, 5, 2. Here we will be having 7 edges and 7 of these. Now while having Bellman fold, firstly we will be having a weight vector or array. Here we have, is it visible? Let's make it here. We are having 6 edges, so we will be having a weight vector of 0, 1, 2, 3, 4, 5. All of them will be having the weight of infinity except this source, that is 0 here. Now we will be considering the order. Here we are having very first as 2, 4, 1. Here we will be seeing we are going from 2 to 4 and then 1. So as in extras, what we will be checking? Weight of parent, that is 2, plus the weight of h, that is 1, should be less than the weight of the child. Weight of the child is 4. But let's consider here the weight of 2, that means parent is infinity. That means we are not still here. जब तक हम एक पर्टिकुलर वर्टेक्स पे पहुंचे ही नहीं है, जब तक हम पेरेंट पे ही नहीं पहुंचे तो हम उसके चाइल्ड पे कैसे पहुंच पाएंगे? So we have to reject this. So before this we should check whether the weight of the parent that is 2 should not be equal to infinity. Infinity, that means int max. While coding, it should be not equal to int max. Why we are writing this? Because in the particular order there is not the possibility that the very first order having the parent is already visited. So before this we will be checking that the parent is visited or not. Then we will be checking the main condition that parent weight plus the edge weight is less than the child weight. Next is 4. Sorry, is it visible? 4, 5 and minus 2. Again we will be checking weight of the parent, that is 4. 4 is already infinity, so we won't be considering the another, that is saving us from the further calculations. Then we have 0, 1 and 5. The weight of 0 is already 0. Then we will be seeing 0 plus 5 less than infinity. It is true, then it will update the value. Now again that is 1, 2, minus 2. The 1 value is not infinity, that is updated to 5. So that is 5 minus 2 plus minus 2 is less than infinity, that is 3 less than infinity. So true, and it will be updated to 3. Now again we will be so the weight will be 2 plus 2 less than infinity, that is 4 less than infinity. So it will be updated to 4. Now in the another, there is the only one iteration in which we have done this much. Now in the second iteration it will be like same order will be considered 2, 4, 1, that is 2, 3 and the value is 1. 3 plus 1, that is 4. 4 less than 3, no, it will not be considered. 4, the value is 4. Value of 4 is 3 plus minus 2, the value is 5 is less than 4, that is 1 less than 4. It will be updated to 1 and so on. So we will be updating the values of the each vertex weight during the v minus 1 iteration, so that it can be relaxed. Now we will be doing the code of this. So the code of Bellman code will be is int v is the number of vertices, and vector int is the graph representation of each edge where it is having size 3, where first is the parent, the second is the child, and third is the weight, as here we have shown the parent, the child and the weight. So here it is the function definition. Now firstly we will be needing a result vector or the weight vector of size v having the infinite value, that is int max, or in sum it is int max 32, except the source value. Source value is here 0, it will be 0. Now the very first thing we will be doing is the iteration over all edges v minus time, that is relaxation or is done v minus 1 time. I 0, I less than v minus 1, I plus plus. Now all edges will be iterated. For auto is a keyword for a particular data type. For any data type, it automatically completes it. Edges. Now int pair is the very first parent, int child, edge index 2, index 1, and weight as h index 2. सो द वेरी फर्स्ट कंडीशन वी विल बी चेकिंग इज कि हमारा जो पेरेंट है वो ऑलरेडी रीच है या नहीं, दैट इज द वैल्यू इज इन्फिनिटी और नॉट एज हियर. सो वी विल बी चेकिंग रिजल्ट pair not equal int max and result pair plus w less than result child, and if it is less we will just update the value of child. So here we have just written the code of Bellman 4. Now let's try to find out the times complexity. Here we are iterating over v minus 1 times, and here we are iterating all the edges. Let the edges be e. So what will be the time complexity of that Bellman 4? Time complexity. The time complexity is order of v minus 1 into e, order of ve, and space complexity is order of v, that is the size of the result vector, that is equal to the number of vertices holding the weight for each of the vertex. Now we will be knowing about the one of the application, how it detects the cycle in the graph. Here how it detects the cycle in a particular graph is we can know while iterating over the graph. For example, I am having a graph 0, 1 and 2, 1, 2, and here it is minus 5. So here we can see there is a negative cycle, that is 1. If I reach there, that is 0, infinity and infinity. So if I will keep on iterating over and over again, it will always keep on decreasing the value of 0, 1 and 2 in each iteration. So how can we detect this particular cycle? So as in Bellman 4 we can say, we have already said, if we have to reach a particular vertex, there is v minus 1 ways. If it is a completely connected graph, so there are v minus 1 iteration. But what if I did the vth iteration? अगर मैंने vth iteration किया और उसके बाद फिर से मेरी वैल्यूज अपडेट हो गई है, that means I had not received a minimum weight, or there is a possibility that I have not received the minimum weight. But if I have done all the relaxations v minus 1 time, how it is possible that I have not received the minimum weight? So why the values is updated if the iteration is done vth time? It is because there is a negative cycle in that particular graph. For example, let's see this example. If I am doing so here number of vertices v is equal to 3, so iterations will be v minus 1 times 2 times. So let's do it 2 times. So here it is 0 plus 1, that is 1, updated. v 1 plus 2 less than infinity, updated. 3 minus 5 less than 0, updated to minus 1. First iteration is completed. Now doing the iteration again, 2 minus 2 plus 1 minus 1, the value is updated to minus 1. Minus 1 plus 2 is 1, that is less than 3, updated to 1. 1 minus 5 is minus 4, updated again. But the v minus 1 iteration is completed. Now doing the vth iteration, that is minus 4 plus 1 is minus 3. So it is relaxing, it is updating a particular value again. So we can say if we are doing a vth iteration and still the value is updated in the vth iteration, that means there is a negative cycle. Because if there is no negative cycle, let's take another example. 0 1 2 1 minus 1 2. Since there is no negative cycle in this one, we can see 0 infinity infinity, the value is updated to 0 to 1, that is 1 updated, 1 to minus 1 0, 0 to 2, that is 0, there is no updations. And again 1 0 to 1, 0 plus 1 1, 1 minus 1 1, 0, 0 plus 2 2, less is that is greater than 0. So there is, that is the value till the second iteration. But now if I am doing the third iteration, there will be no changes in this particular graph. That means there is a no negative cycle. So we can say if there is a particular graph having a negative cycle, if the vth iteration is done in that particular graph, and we can say all the edges are again iterated vth time, there if there is an updated value, the graph is having a negative cycle. So if you want to so if you want to check our negative cycle in a particular graph, then we uses the, sorry, here it's a negative cycle, we uses a Bellman-Ford algorithm. Now the last topic is difference between Dijkstra's and Bellman-Ford algorithm. So very first is, it works with both directed and undirected graph. Undirected graph जो हमारा बेलमैन फोर्ड जो डायक्स्ट्रास है हमारा, दैट वर्क्स विद बोथ टाइप्स ऑफ ग्राफ्स, दैट इज डायरेक्टेड एंड अनडायरेक्टेड ग्राफ. Sorry again. And now coming to Bellman-Ford only works with directed graph. Now the second point, the Dijkstra's do not work with negative edges. There is some cases that the Dijkstra's can work with the negative edges if and only if there is no negative cycle exists. Because if the negative cycle exists, the values will be keep pushing to the priority queue, and the loop will go to the infinite loop and it will dump the code. So it can work in some in some cases where there is negative edges, but not in every. But Bellman-Ford's work with all graphs with negative edges. Third, cannot work with negative cycle graph or can't detect them because it goes on in a negative loop and the code will dump. So we cannot break or cannot find at what point there is a negative cycle, but we can detect a negative cycle in graph using Bellman-Ford, and we have already learned this particular application here. So now a bit small overview. The last one is what here the starting with Bellman-Ford algorithm, what are the major application of this algorithm is to find the shortest path for a single source via weight of the edges to find the shortest path from a particular source to a destination via weight, considering the weight. And second is to detect the negative cycle in the graph, which we have also considered both of the applications. Now, why we need this algorithm instead of having BFS and Dijkstra's? Why still we wanted or needed that particular algorithm? The very first, why not BFS? Because BFS does not consider the weight, or only works with if the weight of each node is same. Works if all nodes weight is same. Sorry for the background. Works if all the nodes edges weight is same, or it only considers the path having the minimum number of edges in between the source and destination, not the shortest path. I also already considered the example. And why not the extras? Because it does not work with the negative cycle or negative edge. Now, how Bellman Ford works? Bellman Ford works by relaxing each particular node v minus 1 times. What is relaxation? Relaxation is also done. Why only v minus 1 times? Because a particular vertex can be reached v minus 1 times if a graph is a all connected graph. So there is a possibility of changing a weight of a particular node v minus 1 times, since it can be reached v1 minus time. Points to consider: the graph should be a directed graph. The second, we have to relax only v minus 1 times. We do not have to change the order of iterations during the relaxations. Now we have considered the logic of Bellman Ford, written the code of it, tries to find out the time complexity and space complexity. Then we have known one of the applications of how to detect the negative cycle, since we have considered both of the application now. And last, the difference between Dijkstra's and the Bellman Ford. Thank you.